class 12. So today we'll be starting with a new chapter, that is the first chapter in your book, that is solid state. So about solid, you already have the idea what are solids. Solid is one of the matter, isn't it? One of the form of matter which has the units, the atoms, ions, they are very closely packed in solid and they are very rigid. And since these ions which are constituent particles or atoms or molecules, since they are very closely packed in solid, they are unable to move. And because of this, they have rigidity, they have definite shape and volume. So that is the idea that you already have. Now today we are going to discuss about solid in more detail. And to understand that, okay, the new topics that is going to be covered, your full attention is required. And hope you will be listening to it very carefully. So broadly, solids can be classified into two categories. Number one is crystalline solid. Number one is what? Crystalline solids. Crystalline solids, and the other one is amorphous solid. So here in crystalline solid, the repeating units within the solid, whether they are atom, ion or molecule, they themselves arranged in a very regular fashion, okay, and they keep on extending in different direction. And here please don't forget, in crystalline solid, this arrangement of these atoms is what? Ordered. It is ordered and it extends to a very long distance, and its arrangement is extending to a very long or large distance. Therefore, these solids, they also have what? It is also known to have long range order. They have what? Long range order. Long range order. Example, NaCl, you have copper, you have diamond. These are examples of some examples of diamond, some examples of crystalline solid. Okay? Now, whenever we come to amorphous solid, before coming to amorphous solid, let me tell you, since this arrangement of atoms or ions are very ordered. Okay? Now, like in NaCl, you have Na plus, Cl minus, Na plus, Cl minus. It keeps on extending towards this side, similar towards below side. So you have Cl minus, Na plus. Look, and if it is Na plus, it has to be Cl. So add Cl minus, Na plus, Cl minus, Na plus. So it keeps on extending in all the three dimensions. Okay, and if you see its extension in the three dimensions, then you come to know that each of these sodium ion is surrounded by 6 immediate Cl minus ions, and vice versa. That means each Cl minus ion is also surrounded by 6 Na plus ions, okay, in its immediate vicinity. And here the force that is acting is very strong. It is electrostatic force of attraction, plus and minus, two opposite charged particles. Therefore, they have what? Very sharp melting point, boiling point. Other properties are very sharp. Now, amorphous solid, here is just the opposite. Here, what you have, the constituent in crystalline solid, the constituent particles were having an ordered arrangement and it was extended to a very long distance. But here, in amorphous solid, it is not ordered. It is not ordered. The arrangement of the constituent particle is not ordered, and the force, and it extends to a very short distance, it extends to a very short distance. Okay, an example here that you have in amorphous solid is glass, plastics, some polymers of plastics like Teflon and others. Okay, Teflon and other polymers of what? Polymers of plastics. Now here in your book you have many differences there between this crystalline solid and amorphous solid. There are a few points. It is your responsibility to go through those points and learn them. Okay, so here I have discussed a few of them. In your book you have more. Please learn them. Now let's move on to more detail within the solid. So that was solid classification. Now we are going deep inside the solid. As we know, our body, the body of a living being is all made up of what? Each unit cell. Each cell. This is our body. Our body is made of cells. Similarly, in solids also, you have to be very careful here. Okay? Now solids has lattices. It has what? It has crystal lattice and it has what? Crystal lattice. We are going to discuss about crystal lattice and unit cell. So let me give you an example. From this example, I think it will be more clear. Like for the building, okay, for the purpose of making the big buildings or flats, what you need? You need to arrange each brick. Yes or no? Each brick in a very ordered manner in all three dimensions. Yes or no? Now, after arranging one brick after the other in all directions, what you need? You get the whole structure of the building. Yes or no? You get the whole structure of the building. Please try to imagine. Here, each brick is equivalent to unit cell. It is equivalent to unit cell, and the structure that you get after arranging each brick in all three dimensions, then what you get? You get some particular structure, desired structure, and that structure is known as what? Crystal lattice. It is the structure that you obtain after arranging each brick in desired in all three dimensions. What you obtain? You obtain a room or flat or the building. That particular structure is known as what? Crystal lattice. So now this is an example. I hope you understood from this example what is unit cell. Unit cell is equivalent to each brick that is repeated again and again to form some structure, and that structure that you obtain because of each brick being repeated, okay, is known as what? Crystal lattice. So let me give you an example. Suppose you have this structure. Now, this structure Q, if it is repeated in this direction, in all the directions, what you obtain? You obtain so many cubes over here. You can refer to the book. Okay, I find it difficult to draw the structure of other cubes. So please refer to the book for this discussion. You have in your book the structure. This side also it is extended. The diagram of the cube. This side also. Here also. In all three dimensions. In all the dimensions, this cube is repeated. Now, once this cube is repeated again and again, then that will give rise to what? Crystal lattice. And each cube which is being repeated is known as what? Unit cell. In your book you have the definition, but understanding is more important. Okay? So each cube is known as unit cell, and this cube, once it is repeated again and again in all the directions, in all the three all 3 dimensions, then what you obtain? You obtain crystal lattice. So you can say a unit cell is the smallest repeating unit, okay, in a crystal lattice, which when repeated again and again in different directions result in the formation of crystal lattice. So each unit, if it is repeating again and again, okay, and then this is known as what? Unit cell. And the structure that you obtain because of this unit cell being repeated again and again in all 3 dimensions or in all 3 dimensions is known as what? Crystal lattice. It's known as what? Crystal lattice. Hope this crystal lattice and unit cell is clear now. Now, in your syllabus, these unit cells, okay, these unit cells could have different structure. Like it could be a square, it could be rectangle, it could be parallelogram. Okay, so it is based on how these atoms are arranged. Now in unit cell, okay, unit cell. Now we are discussing that portion. This is very important. So unit cell can be broadly classified into 3 or into 4 main types. So classification of unit cell. So unit cell classification. We are discussing about classification. It can be broadly divided into 4 different types. The first one is primitive or simple cubic unit cell. Primitive or simple cubic unit cell. Number 2 is body centered. Number 3 is face centered. Number 4 is end centered. Okay, so now here you need to understand what does it mean, primitive or simple cubic lattice. What does it mean? It means that we are discussing about unit cell of a cube system. So here in case of primitive unit cell, each constituent particle, that is, it would be atom, ion, molecule, whatever. Okay, they are located at the corners of the cube. So here, how many corners are present? Here, 8 corners are present. Therefore, in primitive, what you have? You have this atoms, the constituent particles, present only at the corners. In body centered, what you have? In body centered, along, see, in all this time, atoms are always present at the corners. Please don't forget that. Okay, in all the time. And in body centered, along with atoms present at the corners, you have the name itself says body center, means inside this cube at the center you have one particular atom or constituent particle present. So in case of face centered, now I think you can easily say it by the name itself, face centered. As I told you, every time the atoms are always present at the corners. Face centered. So in each face it has one. In each face, means at the center of each face it has one atom. How many faces are present? One up, 1, 2, 3, 4, 5, 6. So it has how many? You can take an example of this particular. Okay, I'm using this chalk box. So here, how many faces are present? If you consider it to be a cube, 1, 2, 3, 4, 5 above and one below. That is 6 phases are present. Therefore, now in phase center, what you have? You have atoms and the phases also. That means one above here, the other that side, center somewhere here, 2, 3, 4, 5, and one is below 6. So 1, 2, this that side, 3, 4, 5, and 6. This is this side. So how many atoms are present? 6 atoms are present at the center of the phases. Along with what? The atoms at the corners. That gives you what? The atom is a phase-centered unit cell. Now end-centered. In case of end-centered, what you have? Obviously, you will be having constituent particle at the corners. 1, 2, 3, 4, 5, 6, 7, 8. And end-centered means at any 2 of its phases out of 6, and at 2 opposite, not any, 2 opposite phases, it will have atoms, the constituent particles. Like if you consider this part, then here it has one constituent particle at the center of its phase, the end phase, then it should be having on the other end of the phase. Okay, so along with the atoms at the corners, it also, in case of end-centered, it has 2 atoms at 2 opposite phases. So here itself, see, this understanding of this diagram is very important. Okay, very important, and this will be used for next topic that we are going to discuss now. So let me tell you here itself. Now, please listen carefully. Okay, this is very important. Here in case of primitive unit cell, what you have to know is, see, each atom at the corner, okay, is being shared by. Now see, this same structure, as I told you, keeps on repeating in all the 3 dimensions. Okay, in all the 3 dimensions. Then this atom will be shared by, each atom at the corner will be shared by, all together, including this cube, 8 cubes. That means this atom, here you will be having another cube here, this side, above, and all together it will be shared by how many? These cubes, it will be shared by 8 cubes. Suppose you have atom over here at this, okay, at this corner, then this particular atom will be shared by the cube present here, this side, 4, then above it. That means 4 plus 4 means 8 cubes. So let me see it once again. Here, if an atom is present at this corner, then it is already shared by this cube. Now, along with this cube, you will be having another cube here. Along with this, here itself, the other one here, the other one here. That means 4 below, and just above it 4. Okay? Please try to visualize it. Okay? If you don't visualize, it becomes a little difficult. Not that difficult. And I know all of your imagination capacity is very, very good. Please refer for this particular discussion. You need to refer to the diagram given in the book also. So as I told you, this particular atom or the constituent particle at the corner is shared by 8 other cubes. Now, here itself, let me tell you, if each atom is shared by 8 other cubes, then that means the contribution of this atom to one particular unit cell is how much? It is 8 divided by 1 by 8. That is equal to 1. Okay? So it is what? 8 into 1 by 8. That means since this particular atom, this particular atom is shared by how many other cubes? 8 cubes. So each, I'm talking about one particular, okay, one particular, then its contribution to one particular unit cell is how much? 1 by 8. Yes or no? 1 by 8. Contribution for this unit cell of this atom is what? 1 by 8. In total, how many such atoms are present at the corner? How many? 8 are present. So all of them, if you take all of them, the contribution of all of them to this particular unit cell, then it will be what? 1 by 8 into 8. Then the number of atoms that is present in primitive unit cell is how much? It is 1. Why 1? I hope you understood it. Because the contribution of each atom present at the corner is 1 by 8. 8 such constituent particles are there. So 1 by 8 into 8 gives you 1. So you can say that one atom is present in primitive unit cell. And this is very important. How many atoms? 1. Similarly, in case of body center, you have 8 atoms at the corners, and you already know the contribution of these 8 atoms at the corners. Yes or no? You already know it. So let me drop this part. I hope you have noted down this side. Now this space will be used for calculating the number of atoms. So we are discussing about number of atoms present in each unit cell. So number of atoms present. So for primitive, you already know it is 1. Similarly here, this is body center. 1 is present at the center. Okay? So you already know the contribution of this 8 constituent particles at the corners. Number 2, number 1, it is already 1. We have calculated here. For number 2 is what? It is body center. I am writing body center. Okay? So BCC, I am writing body center cubic cell. So to be a body center cubic cell, atoms has to be present where? At the corners. 8 atoms or constituent particle. We are going to write constituent particle. 8 atoms at corners plus 1 present at the center of this particular cube plus 1 atom at the center of the body. Center of the body. So this part we have already calculated from this primitive unit cell. That is contribution is how much? 1. So here in case of BCC, the contribution of these 8 atoms at corners is how much? 1. And this 1 atom is present where? At the center of this cubic cell. Now see, to understand this, suppose now this is the constituent particle, and if it is present at the center, inside the body, okay, inside the body, which is deep inside, so will this particular cubic cell share this particular constituent particle with other unit cell? It's impossible. Because what? Because it's present within the cubic unit cell, which is inside. Therefore, this particular constituent particle, this constituent particle present within the body is its sole property. Means it is not sharing with any other. Therefore, the contribution of the atom or the constituent particle, if it is present inside the body, then that means it is not sharing with any other unit cell. Therefore, its total contribution to this particular unit cell is taken, and hence you have 2 atoms. This one we have already seen. This one, how it came? If it is deep inside your body, you are not sharing with the food that you have already eaten. It is inside your stomach. Will you be able to share it with your friends? No. That is your all. That is all the units, isn't it? Therefore, whole of it. One atom to itself, not sharing with any other unit cell. Therefore, total contribution is 1. Therefore, 2 atoms are present in BCC. Hope this is clear. Now let's discuss about this phase center. So in case of phase center, you know, in case of phase center, FCC is number 3. In case of phase center cubic cell, you already have 8 atoms at the bottom. This one had 8 atoms at the bottom plus 6 atoms at 6 faces. Okay, so 8 atoms at the corners plus 6 atoms at the 6 faces. Now let's see the contribution of the 6 atoms at the 6 faces. This part you already know it. 8 atoms at corners will give you 1 atom for each unit cell, and the 6 atoms at 6 faces. Now for that, to understand, you have to take again the example of this. Okay, so if suppose you have 6 faces, now if this is the constituent particle, and if suppose, since this is visible to you all, if suppose this constituent particle is present at the center of this side, this face, then this particular constituent particle, if it is present at the center, then it will be able to share with this particular constituent particle, will be shared with another cube. This one present here. It is being shared with this cube, and suppose this chalk box is present here. That means this will be lying. This particular constituent particle will be shared with between 2 cubes. It won't be able to be shared with any other cube. Therefore, now this constituent particle is being shared with how many cubes? 2 cubes? Yes or no? 2 cubes? Yes? So, I hope you understood from there. Now, contribution will be what? How many faces are there? 6 faces are there. Total 6 atoms are present. And each atom is being shared with how many? 2 cubes. Therefore, the contribution to each cell is how much then? Half. Did you understand? 6 phases, and since each constituent particle is being shared with between 2 cubes, 2 cubes, so that particular constituent particle contribution to each cube is how much? Half, isn't it? If this particular constituent particle is being shared between these 2 cubes, and the contribution of this particular particle to each cell is how much? Half. Therefore, we have 6 phases, 6 atoms, contribution is half. Therefore, we have now 1 plus 2 1 to 2, 2 3 is 6, that means 1 plus 3 equals to 4 atoms. Okay, this is very, very important. So, in your book, you have calculation of number of atoms in primitive phase center cubic cell, and the previous one, that is body centered cubic lattice or cell unit cell. Its unit cell is their unit syllabus, and this is very important. Okay, you need to understand this because numericals will be asked from this particular portion. Hope you understood. If you have any doubt, please, you are always welcome to ask me. You are always welcome to ask me. So, this was for today. We'll be continuing in our next video. Till then, keep practicing, keep imagining,